Thank you for to the organizers of this opportunity to present my PhD work with my two supervisors, Marcello Porta and Ieri Mastropietro, everybody very well. Okay, with the work of my PhD with my two supervisors, Marcello Porta and Ieri Mastropietro, that everybody now knows very well. And we study a model of the conformal factor. It was already explained very well by Stefan today. And it's a quantum effect in the sense that it emerges from, let's say, extreme conditions, usually at very low temperature and very low magnetic field with the two-dimensional insulator. And it's a phenomenon of exact quantization when there is a quantity is exactly quantized in the sense that it measures and it's an integer multiple of fundamental constants. And but I'll focus on a dual description because one of the simplest models to try to understand the effect is the Landau Hamiltonian. It is just composed by two electrons, so the Laplacian, and a magnetic field which is also organized to the plane. So there are three electrons with a magnetic field, and each one computes the spectrum of the Landau Hamiltonian. What is obtained is Landau levels, which are discrete levels separated by integer multiples, and they are infinitely degenerate. And in this picture, we have the energy in the vertical axis, while in the horizontal axis, we have position. So ideally, there is one different eigenmode, one different eigenvector for each position, let's say in the x1 direction. But in physical samples, we have finite size, not infinite size. So we must imagine that there is some confining potential of some kind that keeps electrons to the sample, and so that they don't run away. And at least at a very heuristic level, at the graphical level, we can imagine that the Landau levels, instead of being completely horizontal and infinite, they are fixed, so that the electrons are confined at least heuristically. And then for a fixed level, we see that for a fixed level of energy, we see that this level intersects the Landau levels in n points, where n should be the exact n of level fixed, of a level completely filled, sorry, if they were infinitely extended. So at least at a very heuristic level, there should be connection between the this n, which as we have seen already is the number of levels filled, and something which happens at the edge of the sample. And physically, there are n modes which transport current at the edge of the sample, where n corresponds to the part conductance. So this number, which is measured, has two meanings. One has a topological meaning, which can be expressed purely in the bulk, and one which is dynamical and localized at the end. So we start from Hamiltonian on the field. Hamiltonian on the field. So we have a lattice field completely discretized. For simplicity, I consider this direction as infinite, but the work actually considers two different edges of the cylinder. And we consider first Ampersand Hamiltonian. So this is the translation invariant in the x1 direction, and it's a quadratic Hamiltonian. Everything will be quadratic in this course. So it's quadratic in the creation and annihilation operators. It's a fermionic Hamiltonian, so this is defined on the fermionic Fock space. And we will suppose now some properties on this Hamiltonian. But I just want to say that we consider our system in a thermal state. So the system of the state of the system is a given state, the temperature index, temperature theta, and chemical potential mu, where this mu is exactly also with energy level that we fixed. And I just want to say now that one of the fundamental objects to study are the correlation functions. And we focus in this talk only on the point function, but it also is not a limitation because our model is quadratic, so all higher correlations are obtained in terms of the two-point function through this formula. And if you have never seen the two-point function without imaginary time, you can just forget it. It's evolution in the additional imaginary time coordinate, and just think that we are considering correlation between 2 points x and y on the cylinder. Yeah, it's a title from when I choose to different level in the two directions. Yes, thank you. It's just a limit L for L here. Both L and we both have the same and they go to infinity. So we suppose that our Hamiltonian is translation invariant in the x1 direction, and it's also finite range, so that x1 x interacts with y for a fixed maximal distance, let's say r. And since it is translation invariant, we can perform a block Fourier transform, or let's say a partial Fourier transform in the x1 direction, so that our Hamiltonian becomes the sum of a different Hamiltonian in one dimension less for each k1. And for each fixed k1, we can consider the spectrum of the Hamiltonian HK1. And we suppose the following, that we fix our value mu of the energy of chemical potential in such a way that in all an interval, in a whole interval, mu minus delta, mu plus delta, so this interval here, the only spectrum of the Hamiltonian is given by eigenvectors which are localized, exponentially localized near the edge. So for each value of the spectrum here, for the corresponding value K, the eigenvectors are exponentially different, are localized near the edge. So in this sense, they are edge mode. And if you're asking why we didn't include any magnetic field, the idea is that already included. So in this expression, which is implicit, is whatever Hamiltonian, the phase is integer, and usually this is obtained by adding the magnetic field and filling for instance, in the some Hamiltonian, like in a Haldane Hamiltonian, filling the spectrum to a level. But just to say that there are concrete examples. But then we study a perturbation of the Hamiltonian which breaks translation invariance. So the most important thing, the most important figure is here that we have no more translation invariance. And as to why we study this, there are at least 3 reasons. One is that every time any kind of disorder added to an Hamiltonian usually is characterized by breaking of translation invariance. So that studying any model with translation invariance breaking can be a first step in better understanding of the role of disorder. But there are also other physical reasons, like in some recent also, maybe there's something, the recent realization on the quantum sector, they are realized with the superimposing two different lattices which are incommensurable. So actually there is a distortion of the underlying lattice of the system which is quasi-periodic. So our perturbation is actually a function which is periodic but with a period which is irrational. So since we are on a lattice and the lattice has spacing 1, the two spacing 1 and alpha with alpha irrational are incommensurate. So there is no translation invariance. And we suppose also that our function phi is analytic, and this implies that when expressed in a Fourier series, its Fourier coefficient decay exponentially fast. This will be important for the following estimate. We have also to suppose that our frequency is Diophantine. It means that is, let's say, it's far from being rational. Because if alpha is rational, then there are multiple terms such that on the torus we go back to zero exactly. So in a sense, being far from being rational, it means that we stay away from zero. Of course, since alpha rational, we still densely the torus. So with the large n, we must get close to zero, but we need a lower bound. So to say that we cannot get close to zero with small n. This is a restriction, yes, but there are two reasons to it. One is that for rational multiples, one can just include enlarge, let's say, the minimal block of the lattice and reduce oneself to a periodic density interpretation by density. And the other one is that it's not a limitation in measure, in the sense that for almost every real number, such inequality is valid with respect constant. So I will just say no proof of such so as to justify the need for a multi-scale analysis. So I will just say that we start with the first Hamiltonian. We take the Fourier transform in both coefficients, and for simplicity I am reducing to just one dimension. I call K and P the Fourier transform in X and Y. And I divide by L because we will get here a factoriality for the translation invariant part. And after the Fourier transform, we get the Fourier transform of the H, which is the translation invariance. So it's diagonal in K and P. And in addition, we get a small, because there is a lambda, perturbation, which is not translation invariant. So at least theoretically, we can try to the solvent or non-active. Okay. And if we pass to Fourier transform in Fourier space, then this product becomes a multiple convolution. So that the and then another coefficient, then the result is T plus N1 alpha plus N2 alpha and so on. So at least theoretically, we can try to consider a first order term and to see what can go wrong. When can this be missing? So this term this term is not singular theory when both terms are great. So let's say that we import the first scale, the argument of the first solvent, and the plus one alpha, they are both such that the resolvent explodes. Actually, remember, mu is on the spectrum of Hf, and the corresponding value of was Kf, if you remember the graph here. Let's suppose that both K and K plus an alpha are close to Kf, so there's both these terms are vicious. So let's say that we are around Kf plus or minus 2 to the minus n, so order 2 to the minus n. But if both these terms are close to K minus f, also n plus alpha must be smaller, because this numbers are, these momenta are close to the same momentum, so their difference must be small. But if n1 alpha is smaller, you can apply direct function to this. You see that n1 must be this. But then you remember that we have so that the time y and 1 is exponentially small in n1, which is small in this case. This is to say that all these expressions is small and there is no problem. So whenever we can do there is no problem. The divergence is only in appearance. But the problem is that we cannot do this every time. Because there are some combination of n1, n2, and n, such as this sum is exactly 0, of course, so there can be. And for this, there is no Diophantine condition, because the condition, of course, is only for n different from 0, because for n equals 0, we get 0. So this term must be treated differently, as we have seen in the course of theory, which is treating them differently will actually mean to localize them, put them in the integrating measures to proceed in a multi-scale analysis with a renormalization. So that with each step we isolate the most divergent term that we can take other way, so we put them somewhat in the method. But I will not elaborate on it. I just want to say that it's crucial to have one term. And yes, I just presented the result here. In the end, we get that the two-point function is completely described by an expression where we have a small remainder term, which is the case plus step and everything else, while the main contribution is given by a term which is localized near the edge. So we have the function which is, so for those who recognize it, is the one dimension, the two-point function for one-dimensional relatively fixed terminals, but whose parameters are renormalized. So we have the wave function of renormalization, Fermi velocity, and a Fermi points which are close but different from the static one of the unperturbed one. And also there is the addition of two same modulations, where both in X and in Y, we have quasi-periodic modulation. So our super function is indeed not rotation one, not rotation one. And yeah. So if I just want to add that with the two-point function, we can also compute the transfer coefficient and get that in the end the conductance is quantized while the susceptibility is not. And I will end here, and I thank you for your attention. And please ask me questions to expand on whatever made me interest you. Fine. No. Yeah. No, here is two-dimensional. At this level is two-dimensional. Yes. Yeah, yeah. At this level, I do the Fourier transform instead of doing it in x minus y. I do it in x and y separately, and I see that I get something which is not. This one. Okay, so the thank you.
Currently not. Ah, okay, it was much easier. It was much easier. Oh, yes. Sorry. My bad. Okay. Yeah, yeah, it was, so it's my bad. So first of all, I want to thank the organizers also for organizing this nice school. This is based on a joint work with Marco Merkel from Memorial University. And so just a small refresher on open systems. So the problem is that you consider a quantum system S, which is interaction with an environment, which we call a reservoir. So our Hilbert space will be bipartite, a tensor product. And we consider, for example, a state, which is a density matrix on this tensor product Hilbert space. So one has a Hamiltonian acting on both reservoir and system, which is the sum of two free terms and an interaction term. And suppose you're only interested in system observables. So if you're only interested in system observables, as has been elucidated in the lecture before, you can consider just a reduced density matrix. So one where you can compute all position values just by the reduced density matrix, which is defined by the partial trace with respect to the reservoir degree of freedom. So what the big question in open systems is to kind of understand this map, which is the time evolution of the reduced density matrix arising from the full interaction between system and reservoir. So in these models, I will consider they are quite simple in the sense that we always want to consider a larger reservoir. So for us, a larger reservoir will be a reservoir which is composed of many identical quantum systems. And just to try and explain this in a specific model, there is this Haberberger model, which is a model of interaction of matter with light, with lasers, which is of this format already been considered in the literature. So we have in the finite number of two-level systems and a bosonic Fock space, and we have a field in interaction with these two-level atoms. So in this case, in the rotating wave approximation, this has been considered. So the notation is just, as Fabrizio was saying, it's acting on the n sector of the tensor. So on the n tensor product. So this model has been already considered by Davies and by Yep and Lieb. So Davies was interested in understanding the regime. So they did the asymptotic behavior of the equilibrium state of the field under the action of many atoms. And he considered the delta equal 1, which is the mean-field regime, which is also what we consider. But he uses a method which is a bit obscure. He just uses the representation of the spin to carry out this limit, and it transforms the mean field limit in a high spin limit and takes the classical limit. While F and Lieb, these articles are very deep and very interesting, but they consider a slightly different setting, which is the quantum fluctuation regime, because they wanted to show the phase transition, again in the equilibrium state of the system, which is the super radiance phase transition. What they found out is in the limit under certain conditions on coefficients and temperature, there is a phase transition, and it basically arises by the quantum central limit theorem. So the infinite atoms become an emitter of coherent fluctuation. So my personal original motivation for this kind of to study these models was that I was trying to extend results by my PhD advisors to study it as a model for open systems. So if one considers, for example, this kind of simplified Hamiltonian given by dipole approximation of a particle interacting with a bosonic field, which is scaled in a mean field way in the sense that the creation annihilation operators are scaled with the square root of the number of operators, as they are morally the square root of the number of operators. So in these models, one can consider this kind of mean field approximation called the classical limit, and one considers so kind of a very weak interaction, but macroscopic states. Macroscopic state means the expectation scales with the number. So, for example, product states and coherent states. And so there are results by my PhD advisors and Marco Olivieri, but it's the same regime basically as the strong coupling regime of the polaron, which has been studied in work by Frank and Schlein. But all these use kind of special states which need propagation bounds, and they are not completely trivial to get if one wants to study. So in open systems, you want to study equilibrium states, and it's well known that if you take an high temperature limit, these are in a sense of mean field type. So if one verifies that with Vic rule with scaled creation annihilation operators, one finds something convergent with a different covariance, which is kind of a classical Gaussian measure. But this is too hard. We have to go out of the Fock space and stuff. So we started with something much simpler, and we wanted to kind of elucidate how an effective dynamics for open systems arises in the models similar to the Haberberger model. So our setting is very simple. We consider, in fact, this kind of Hilbert space, which with n copies of a reservoir, which we can embed in the Fock space, but we use only trivial methods, very easy methods, so it's not needed. And we consider this type of Hamiltonian with the mean field interaction. So the question is, what is the effective limit in this case when one takes the n to infinity? And so this is kind of finding an effective model in open systems. The most famous one are all Markovian models, which are on the weak coupling singular coupling, low density limit, and this is a different. So our idea was to kind of showcase a different effective model. So in a smaller refresher, one can define the mean field observables or effective or extensive observables, which are just given of the average of the operators each acting on a different tensor. So the main properties of these mean field observables that they are asymptotically abelian, as is well known. This means that if I take the commutator of two mean field observables, I get a mean field observable in which I gain a power 1 over n. So what this is telling us is that this is a mean field limit. So if you want suitable states, for example, product states, once it's formally that this scales as 1 over n. So the mean field limit is a classical limit, which is a very well-known thing. In fact, the question is what are the states which are suitable for this. So the states which are suitable, these are symmetric states, which are, so we consider in the density matrices, the families of density matrices, which have these consistency properties, and they're symmetric. So symmetric just means that under the perturbation, the expectation of product observables do not change under permutation, and one takes the partial trace over k hyperspaces, then one gets back the density matrix one expects. So these are very old results, very well known, and this is called the quantum definite theorem, because it's an analog of the classical probability theorem, which tells us that there is a unique probability measure over the set of pure states, which is invariant under the U1 action, which represents all the density matrices by a unique measure. So this really goes back to Ruel, Stormer, and then more recently this has been further elucidated even with quantified version of this theorem by Lewin and Rogerie. But I will do something much easier. So for our assumption, the model, let's consider initial states product type with symmetric density matrices, and let's consider our interactions to be bounded, just for simplicity, because so our theorem basically states that one can put convergence of this density matrix to an average over unitary evolutions, which are time dependent and depend on a parameter f, which is comes from the decomposition of the original density matrices, consistent density matrix we are considering, while the unitary operator is just generated by this time dependent Hamiltonian, which is just the interaction we had with which arises with the elastical limit, the mean field limit of the interaction. So we get exactly the expectation of the mean field observables for the time evolved f. So this is basically saying that what was our reservoir evolves freely, kind of, so it evolves under the action of the single particle Hamiltonian, and then we take the expectation of the observable. So the proof is trivial, so one can restrict to just one operator and product state, and defines time evolved operators, goes to the Dyson series, expands everything. So we are doing something really easy, expands everything, and with our assumptions, everything is absolutely convergent. And in each, we expand each commutator, we look what kind of terms we get, and we get terms of this kind. So this is a trivial combinatorial argument to observe that what you have in the limit, what happens is that the only terms which are preserved are the ones which each single site operator acts on a different tensor, because by counting arguments they are exactly n to the k with a 1 in front. So all the other configurations which you can have kind of non-trivial correlations for two different time evolved operators vanish. So this is actually one takes the limit and sees that basically only these terms remain. So this is interesting to me because it tells us what's actually being done by this effective model for open systems. We are discarding basically all correlations at different times and keeping only this kind of products, which is a more severe version of what actually happens in the weight coupling limit, in which you assume you are on time scale where the correlations inside the reservoir vanish. So this is why we get a much simpler dynamics. So one works just resonates the Dyson series, and in this case just gets this kind of the effective Hamiltonian. So we want to find out that the dynamics is generated by this effective Hamiltonian. So the question is, recall I wanted to understand this as a model of open systems, an effective model of open systems. So the question is how interesting is it as a model? And it turns out that it can be either you're a physicist or not, so it's either interesting or not interesting. So basically what one can show is trivial, that if you split your system into two subsystems and you have interactions which are separately on the systems of systems, sorry, the evolution becomes trivial, so it becomes a product of unitaries. And this means that there cannot be created correlations to the reservoir, which is something which is actually present without taking the limit, even for very simple reservoirs. So what this tells us is that this is not, so if one takes just the product states and this kind of unitary evolution, this is not very interesting because we are not looking at anything interesting in the limit. And one should do something else, which is in fact take some thermal distribution and hope that the average of the classical measure drives some the coherence or increases the entropy. So obviously one can extend our proof in a ugly way, which is just we assume that we can do all the operations I said, so we can carry out to the limit because everything is bounded. And these are conditions which ensure that, and it becomes a game of proving these conditions in different models. And for example, one can do it for bosonic fields. So this kind of unbounded operator are okay, and if one can consider coherent or quasi-free states, and this works. So obviously one can consider also states which are not completely symmetric. They are a bit different. For example, there is one can consider states in which you rate correlations on a finite length by EM, which is for example a quantum channel. And as long as the length is kept finite in the limit as n goes to infinity, this washes out. So you cannot see it, and you just see the rho in your effective potentials. Or one can consider a macroscopic number of different states, and one in the limit gets just a density matrix with the ratios as coefficients. So I think I'm actually a bit late. So in brief, we wanted to showcase a very simple regime in which one can find the effective theories for quantum systems. And we used a very basic method, which, so the idea is that this method does not require propagation bounds on anything. And in fact, by using the same argument, one can prove the convergence to a quasi-classical limit of the spin boson Hamiltonian in the high temperature regime with this coupling, scaled in the way I showed you. But a more interesting model in which you have a rational particle living over R, would require some smarter bounds, so it doesn't work. So in fact, this is really different from known Bohr-Markov approximations. And so we have a limited effect on the system. If we don't consider states which are distributed over the whole, if you want, lattice of the reservoir. So these quasi-classical models, if you want, in which you get an effective description of an average of unitary evolutions. is not completely understood. These are models for classical noise. It's not completely understood what kind of behavior can drive in the system. And we have shown in a different paper what are the effects on the coherence for some explicit reservoir, but this is only possible in an exactly solvable model, as it often happens in the system. So an interesting topic will be to try and understand how to extend this result actually in the near field approximation of matter radiation interactions for a bosonic reservoir in a high temperature limit. Also because this is actually this high temperature regime is something that physicists actually use, and they derive formally a high temperature master equation, which has never been derived, and it's an ill understood problem. So I thank you for your attention, and your questions. Yeah. Okay, yes, you should say a couple more words. So actually, the deformation model is actually used in matrix. Yeah, for example. So there are that. This basically models some optical traps. Is not completely unreasonable, but really this is a training ground for looking. So it has the same structure as the mean field approximation of matter radiation interaction. But anyway, yeah, the deformation model it's very, yeah, it's actually, so if you have time, you should take the Italy papers to get deep interest.
Okay, well, first, thanks for the opportunity to give this talk here. As you mentioned, this is funded by this research initiative of the Deutsche Forschungsgemeinschaft, where I'm a part of as a PhD student at the University of Munich. And this is part the joint work with Lukas Junge from the University of Copenhagen. And this picture was taken from the Eiffel Tower, so you can see like the view over Paris. That's just this weekend. Okay, so here's the system. We look at the dilute Bose gas. So we have n identical bosons in the box. We have in this case there's no sign here. We've heard a lot about fermions. Now we talk about bosons, so there's no sign here, which leads to some interesting property, which I will talk about just in a minute. And then we have the Hamiltonian here. With a kinetic term and an interaction term. And for me, the interaction term should be positive, radial, and complexly supported. Of course, these are not necessarily physical assumptions, but it makes the analysis way more feasible. And then if I look at this Hamiltonian, well, if I want to understand the system, well, I should understand the spectrum of the Hamiltonian. If I know the eigenfunctions, if I know the eigenvalues, I can very well describe the system. And well, for example, and this is what Bose and Einstein have done pretty much 100 years ago in 1924, 1925. Well, they considered a free system. So let's forget about the interaction for a moment, see what happens. And then we see that the system actually it has a very trivial eigenfunction. You don't need to take these Slater determinants, because for bosons, all particles can be in the same state. So the ground state is if you have all particles being in the same state, namely just constant, because then if you act on this with the Laplacian, your energy is 0. And then they discovered theoretically this phenomena of Bose-Einstein condensation, let me say here in the thermodynamic limit, which is defined as you count the number of particles that are in the ground state. So it could still happen for some reasons that are particles that are not in the ground state. But in your system, you count the number of particles in the ground state. You look at the fraction, so n is the number of particles. So you look at fraction, and then you say, if this is always positive, even in this thermodynamic limit, which is the limit where you take the box size and the number of particles to infinity while keeping the density fixed, if there's a uniform lower bound, then we call this Bose-Einstein condensation. And in the free system, it's not a hard proof, so you can easily follow the papers and check that this is true. But it was merely believed to be a theoretical observation, right? So I don't know, having system with no interaction, that's not really physical. And then it was a bit of a surprise when in 1990 it was actually observed in interacting systems by two different groups, which led to a Nobel Prize for both groups. And this is well, a nice picture that they got, which was on the cover of Nature at some point. And what you can see here is rubidium atoms, the momentum distribution of these atoms. And here at rather high temperature, this is what you would expect, right? There's some particles in the ground state. It looks like a Gaussian. That's what you would expect at some temperature. You have a Gibbs state, momentum distribution is like Gaussian. And then you cool it down, so temperature decreases here. And then there's some critical temperature, and suddenly a macroscopic fraction of your particles jump into this zero momentum wave function, this U naught we just said before. And then, okay, if you wait for a little bit, then all of the high temperature particles evaporate. So this was very surprising. And it has been an outstanding challenge to prove this for interacting systems. Right? Even, okay, I don't know when people really started trying, but at latest 1990, when they saw this experimentally, they started trying to prove this. And it was showed to be a very difficult problem. It was not proven until now. So what we instead will do is, well, if we cannot understand the eigenfunctions, maybe we can understand the eigenvalues. And one way to understand the eigenvalues is if we look at this free energy. So the free energy in the thermodynamic limit, normalized so per unit volume. What is this F? Well, it's just the log of the partition function. And the partition function, it has all the information on, or maybe in an average sense, it has a lot of information on the eigenvalues. And well, we want to show a formula on this F in the dilute limit. So when the density is small. And the first thing you observe is, well, there should be some interaction. The leading order energy, if you think of it, might be if you look at two particles interacting and then just multiply it by the number of particle pairs that you have. So how can we describe the two-body interaction? You look at the scattering equation, which exactly describes interaction of two particles. And you see that, well, at least as soon as you're outside the support of your potential, your F in 2D, now in 2D, should be like a log. Okay, and then there's this funny parameter A appearing here. So this is maybe the definition of A, which is the scattering length. So it models how two particles interact. And then there were some results on this free energy. So at zero temperature, where the free energy actually is just the ground state energy, you find this formula. So as I said, we look at the dilute limit. So it's an expansion in this diluteness parameter y. So y is here. If rho a squared is small, then also y is small. So the first term is this one. It's order rho squared y. Then you find a smaller term, which is rho squared y squared log y. You find an even smaller term, which is rho square y square, and you can maybe go on. This was conjectured in the physics literature. The leading order was proven by Lieb and Ingmarsson, so that's the leading order. And then the second order was proven by this group from Copenhagen quite recently. So that's the zero temperature result. What do we know at positive temperature? As we saw in the picture, there's sort of a critical temperature, at least in 3D, where below this temperature you would just expect condensation. In 2D, it's not so clear. You don't really have condensation. There's a similar thing physicists call superfluidity. And it appears if you're below this critical temperature. So if you're below this critical temperature, there's this result, which was proven by Deutschert, Meyer, and Salvinger in a series of 2 papers in 2020. And you have the free energy of the non-injecting gas. And then you have a term which comes in because of the interaction here. And you see this temperature term. So if I expand this, okay, let me take a T20 limit here, then this term vanishes. And if I take T20 here, well, this is just 1, and we get a 4 pi rho square y, which is exactly this. Oh, sorry, delta is 2y. Okay. And what we then proved is kind of an extension of this formula here at 0 temperature, together with Lucas. It's not yet on the archive, it will appear soon, hopefully. So if T is less than the critical temperature, and if this diluteness parameter rho s squared is small, then what you find, so far only as an upper bound, we also will prove the lower bound hopefully at some point, is that as an upper bound you get the 0 temperature term, and then you get this temperature correction term. And then there's some errors. And the form here looks already a little bit like this trace of the partition function that we saw before. Maybe we will see in the end why this is reasonable to expect something like this. And okay, let me give a quick proof overview and maybe some more details later. So first, we need to localize the smaller boxes. The idea is that it's very difficult to prove things in a big box because mostly because you want to use the gap that your Hamiltonian has, and in a big box, the gap scales like L to the -2, so it's very small. So we go to smaller boxes, we find some method, or there is some method, it was there before, which helps you to patch the boxes together. So that's the first step, which allows us to go to a smaller box. The second step is about implementing correlations. So we saw that there was this the scattering equation, and there's some way with the Chester factor, which allows you to modify your Hamiltonian a little bit so that you see scattering. And then the third step, once you have this renormalized Hamiltonian, so after you implemented the correlations, you obtain a so-called quadratic Hamiltonian. You will see it on the next slide. And we aim to diagonalize this because with diagonal Hamiltonians, we can work pretty well. And let me here flash some comparison to the 3D case. We proved a very similar formula together with Heinz-Lam, Schlein, and Trier in 2023 and 2024 for the 3D case. So it looks very similar, right? You also have this T equal to 0 term, you have this temperature correction term, then there's some error terms. The main difference is 3D is harder. I will show you why in a second. And we cannot go up to the critical temperature. We have to stay quite far below the critical temperature because rho is a small parameter in our system. We're quite far away from the critical temperature. And there are multiple reasons for this. So maybe let me talk about this point first. If I look at 2D, I didn't tell you yet what is L is, but in 2D, just believe me, for this moment, it scales like y to the -3. So y to the -3, it was like the log rho. And if you do the same thing in 3D, you see you get a rho to the -1/2. So in 3D, you have much more particles than in 2D. And that's the reason the analysis follows. More differences in 3D. So I told you this intuition that the leading order should be just the two-body energy times the number of pairs you have. This is true in 3D. It's not true in 2D. So here you have to be a bit more careful in 2D. You saw the scattering equation, which was like a Laplacian F is something else. So if you look at this in momentum space, if you invert it, you see that your scattering equation goes like 1 to the like 1 over p squared, which is not an issue in 3D if you integrate it around 0, but it's a big issue in 2D. So in 2D you need some you need to be very careful. Things are becoming distributions suddenly, so that makes your life harder in 2D. And the last thing we added is this here, maybe more common for the experts, that if we use the Weyl transformation, we actually have some continuity here, which allows us to make the localization exact. In previous papers, we had inequalities. Now we actually have an inequality in the localization part. Okay. When did I start? 7 minutes. Well, wonderful. Okay. So in 7 minutes, I can give you more information about the proof. So I talked about these 3 things very briefly before. So let's dive in a bit deeper. There we go. So how do we do this localization? We have this big box, so that's the thermodynamic box lambda. And then, as I said, it's very hard to work in this box. We want to go to smaller boxes, L. It's rho to the -1/2, y to the -alpha. And in the end, we want an upper bound. So we need trial states on these boxes. So what do we do? Well, if we had a Dirichlet boundary condition on the small box, we could take one trial state and then just patch them together. On the other hand, it's much easier to work with periodic boundary conditions on a torus. So what we do is we take a slightly smaller box, this blue box. On this blue box, we work with periodic boundary conditions. And then we take a little bit like a corridor here, which has two meanings. So first, it allows us to go from periodic to Dirichlet boundary conditions. And secondly, it's bigger than the support of the potential. So in fact, these 2 boxes here, they don't interact with each other. And then small side remark. So actually, we work on these boxes in the grand canonical setting. The problem was posed in the canonical setting, so there's another quite standard way to switch between the two ensembles. Okay, so that's about the box. Next thing, now we're on the small box. What do we do with the correlations? It is enough to multiply our trial state with the Jastrow. So maybe it's time for And the way we do this Jastrow is we just take product of this scattering solution F, which we saw before, and you can compute what the Hamiltonian does with this F, and you actually see that you regain the scattering equation. Now it's with a factor 2, and it helps you to change this potential V, which you had in the Hamiltonian, into a potential U. And the nice thing about the potential U now is that its integral is 4 pi y, or 8 pi y, or 4 pi delta. And this is exactly what you saw in the expansion of this free energy formula. And as a side remark, so there was also this entropy term in the free energy, and of course you need to make sure that by multiplying this transfer factor, your entropy doesn't change much. And then the last step is this diagonalization. So the script U, and this U here, it's a two-body potential. So it's pair interaction. Yeah, pair potential. Yeah, so the V is a pair potential, so it's a V. Okay, but okay, yeah. So you see it here. This was a Hamiltonian. I write it now in second quantization. We saw it a little bit already. Maybe what do I want to say? It's just a different form of writing the Hamiltonian. You introduce these operators. You see this is the kinetic part, like a p squared, and here you have the potential part. L is large. So exactly, it's the inverse of the density is small. Of course, it's much smaller than the thermodynamic length scale, which the problem was originally phrased on. But in fact, all of these quantities are very large. Delta is the smallest parameter. It's like 1 over log rho a squared. Okay, they satisfy the CCR. And then since you renormalize the potential you had here, you can treat this potential more or less perturbatively, right? You know that most of your particles are on the ground state. That's what we saw in the picture in the beginning. So you can start and think of this like, okay, what if I have only zeros here? So what if in my potential, I only look at interactions within the condensate? That's your leading order term. You can pull it off. Okay, so that this will give you a constant. What if there's only one zero momentum here? That cannot happen because we have momentum conservation. And then let me go from the other way around. If there's 3 or 4 non-zero momenta here, which means that you look at particles interacting outside the condensate, this will be very small because there's very few particles. So you can more or less throw them away, and you end up with a quadratic Hamiltonian. So it only has an A star term and an A term. And this you can diagonalize explicitly. There's a nice theory by a quadratic Sobolev transformation and a C number substitution or Y transformation. And oh, sorry, now here's P on the board it's U. So the script P and the script U are the same. And what you find is if you apply this unitary transformation to your Hamiltonian, you get a constant term, and it's exactly the term that you want. And then you get a quadratic term. And this is almost like a free problem now, right? The free Hamiltonian would just be p squared AP star AP, this guy. And now it's maybe a bit shifted, a free problem. And this you can treat very easily. You compute like you get a Gibbs state from this. You can compute the partition function of this Gibbs state, and this is exactly so this will be the dp, which is on the board. And this will give you exactly the temperature term that you saw in the formula on the second slide. And I think this is all I wanted to say. And thanks for your attention. Say it again. Yes, we define the F as being you take a scattering solution and you cut at some point. Okay. No, it depends on the cutoff, but too little I mean, this is an approximation, right? It depends on the cutoff, but to subleading order. Yeah. This is the Fourier transform. Yeah, Fourier transform. But you see, if you in here, the stupidest thing that you could do is just insert the constant wave function. In the Hamiltonian, this would be an upper bound, and the upper bound would be, well, okay, maybe you see it better in the original formulation of the Hamiltonian, but in the Hamiltonian, you just test against the constant function, you get exactly integral of the potential as a. Yes. So U is a okay. So U is a function on the torus, but it's compactly supported. You had it as a function on the left. Yeah. No. It's sorry. Delta is not the Kronecker delta. Delta is my diluted parameter. Yes, that is parameter. Now it's defined what I think I define y and then speak from delta to y or something. Yep. There's a yep. Okay. Mm-hmm. Mm-hmm. Okay, so first about this this L, maybe the best way to look at it. And if you look at the free Hamiltonian, your first okay, one body free Hamiltonian, just a Laplace on a box. Your first eigenvalue is 0, and then your next eigenvalue is 1 over L. And you want to at some you kind of want to treat the potential as a perturbation of the free guy, and therefore you want to have a spectral gap. The gap cell, or 1 over L. Yeah, and this cannot be, if this is too big. If the gap is too small, you lose. That's where the L comes in. No. Proving well, yes, what? It's not a finite volume, right? Yeah, for finite density, I'll define it. Yes. Yes. And then the second question? Yeah, I guess now in this. Yeah, definitely. I mean, there's error terms which no, I don't have them on my slide. And then no. I can show them later if you want. Well, actually not, right? If your potential is decaying fast enough, then you also don't care. But it becomes a bit more technical. Yeah. Probably it will be.